Hello, welcome back to the continuing lecture series in investments. So, in our last session, you saw how value at risk can represent and how value at risk is calculated, and how at different percentile level under our four scenarios, right? How these value at risk would can be also used to. At the last part of our video, I briefly talked about whether that estimate of value at risk is exactly conforming to what is normally expected based on normal distribution, or whether it is exaggerating or based on normal distribution assumption, right? Based on probabilities by normal distribution, right? So if you remember that, then this is a very critical point. Why? Because how do we take how do we take that how do we take that forecast as normally expected? In other words, our assumption, first of all, what did I say? Four states of the economy. That's quite plausible, but how likely are the probabilities assigned to them? Right, 5%. Remember, 5%. Severe recession, 25% mild recession, 40% normal growth, 30% boom. And think about it, our expected portfolio return and variance all depend on these probabilities, right? And are these, expected returns, not portfolio, but, it's portfolio, but, under each scenario, how likely are they to be the most likeliest cases, right? First of all, four scenarios are very discrete, and there can be, think about it, can there be only four cases? Of course, these four scenarios are very representative states of the economy, but the reality is that in reality there are so many gray areas in between, right? So in other words, these four states are very discrete, but the reality may be more diverse or more varied. So to have a normally distributed outcomes, in other words, for the the results outcomes to be this smooth, it has to be continuous. In other words, it has to be a continuum. All these different states must be a continuum, right? Not discrete, 4 states or 8 states or 16 states. But think about it. The more scenarios, more varied scenarios are there, right? The more varied scenarios there are, the more, the smoother these, results will be, right? Because the more varied states, the states of the economy, or the more varied scenarios, the more we can construct, more smoother distribution of the expected returns, right? So it's a very critical question whether the returns are really normally distributed. Okay. So the monthly returns are normally distributed. Let's say if monthly returns are normally distributed with a mean of 1%, right? I mean, any random variables are normally distributed, right? In other words, if you just walk down the street, a busy street like 42nd and Times Square, and randomly sample 100 people. I mean, wouldn't this be a very random sample of average person in the United States, right? It won't be only just a random sample of average people in the United States, but I mean, all over the world, the global random sample. Because why? Because 42nd Times Square, it's a tourist hub, right? You will find all people of all races, all ethnicity, all age, all gender, 3 genders, all genders, maybe 3 genders. I don't know if there can be 4th gender, but let's say 3 genders. And so all race, all age, all heights, all weights, right? All income, of all different income levels, And if you randomly, there's a very good chance if you sample 100 people from Times Square, 42nd Times Square, most likely you will get a very, a randomized sample. Isn't that right? So just like that, and that's monthly returns are random variables, right? And especially, think about it. Daily returns are very random occurrence, right? Today's return is not necessarily correlated with yesterday's return, right? And tomorrow's return is not necessarily correlated with today's return. What determines the daily return is some shock, or positive or negative, right? The information that was previously private, which becomes now public, right? In other words, news, a shock, right, to the market. So, who would have ever thought thought that the market was rallying, until even, the day before. And then from yesterday, the news about, uh, stimulus, stimulus package, turning sour, right? Uh, in the Congress, and as um, uh, the Secretary of, Treasury, uh, there's, bad news, kind of adverse news about the uh, another round of stimulus package. Then, uh, until then, the market was rallying, and then suddenly this news broke out, and then, since yesterday, the market is kind of tanking a little. So all these things are, I mean, has all these things have nothing to do with the company's fundamental, right? Has nothing to do with each company's fundamental, but just, um, uh, a random shock to uh, the market. So day-to-day returns are clearly random variables, so they are like, coming from the random sample, right? Any number can happen. It could be, 10% yesterday, but today 15%. And tomorrow, the day before yesterday, I mean, it was, 8%, 10%, today 15%. So you think, oh, there's some positive trend. Nothing guarantees that on day-to-day basis. Today, then it can be, -5, right? So returns over very short-term periods, see, returns over very short time periods are normally distributed because they are random variables, and a holding period returns up to 1 month can be treated as normal. Right? Let's take a look at this. Suppose monthly return is normally distributed. This means normally distributes wave sign, and ND means normally distributed, right? That looks like distribution, right? With mean of 1%, right? Then expected annual return will be 1.01 raised to 12 minus 1, right? Annual return is the compounded result of the monthly returns. So annual return is a nonlinear function of monthly returns. And are they also normally distributed? No, it's a matter of fact. Nonlinear functions, right, are called are chi-square distributed. It's called chi-square distributed. Chi-square distribution has a like skewed, to the left, meaning, a more most of the outcomes are more, clustered towards the right tail. Why? Think about it. Even something squared, right? Something squared, anything squared, any number squared is always positive. There is no negative, isn't there, right? There's no negative number, right? When you square a negative number, it's still positive, right? So the results will be pretty much, clustered towards the right tail or right side of the distribution curve, or rather, but it's called, skewed skewed to the left. I mean, the tail side. Where will be the long tail? The left side will have a long tail, right? Wherever there is, it's called skewed, right? We have. So this is called left skewed. chi-square distribution is something like this. Now, so annual return is clear, may not, normally distributed. If we extend this logic, isn't monthly return also normally distributed? Isn't it not normally distributed? I mean, mathematically, monthly return would be a daily return, 1 plus daily return raised to 30 minus 1. So is it normally distributed? It doesn't look like it's going to be normally distributed, right? Because it's nonlinear. It's a power function. Still, however, daily returns by themselves are random variables, right? And normally distributed, and they are random walk. Random walk meaning, it's really, a Brownian motion. It's crazy. You look at, a daily, one-day trading price movement graph, by the minute, by 5 minutes, even by 5 minutes. During the day's transaction, it's crazy. It's so random. But daily return. If the daily return is normally distributed, holding period return up to 1 month can be treated as normal. Why? Isn't it like actually it can be treated as normally distributed? Why? I mean, why? Because it's not exactly like this. As I said before, at the introduction, I said all daily returns are really random and crazy, right? And then but tomorrow's return is not necessarily the correlated result. Result correlated with today's return, and today's return is not necessarily a correlated result correlated with yesterday's. And yesterday's return is not necessarily correlated with the day before yesterday. They are really like random. So monthly return is not necessarily 1 plus daily return raised to 30. I mean, theoretically, it should be, but in reality, it is not. And also another reason, I'm going to get to another reasoning behind it. So even, holding period return, long-term holding period return, is normally distributed by using continuously compounded rates. Think about it. And I also why continuously compounded, using continuously compounded rates are important, because it would emulate that smooth curvature of smooth curvature of the normal distribution function. In other words, distribution of highly dense and highly dense continuous random variables are normally distributed. The chances of normal distribution would go up if the data are continuous and densely distributed, right? But let's go to our empirical evidence, or this is also theoretical, but also empirical, because we are inductively this is inductively proving why it is so. Suppose on annual basis, continuously compound return has a mean of 12%. Effective, then effective annual rate how to find effective, and without, let me just quickly go over to see. Continuous compounding, right? 1 plus effective rate, which is, basically, exponential Euler's number raised to APR. So, I mean, by the same APR, then, if you want to solve it for APR, then you have to take the natural log on both sides, right? And then, and it's the same for the compounded, continuously compounded rate, right? If you want to solve for EAR, then E raised to continuously compounded rate minus 1. So by that, was, so this is the compounded effective annual rate, which is, which is equivalent to a continuously compounded rate. In other words, to get the same result, get the same future value as 12% continuously compounded rate, then one-time interest rate that would take you to the same future value as continuously compounded future value is 12.75%. Make sense? Now, the difference between the two is 75 basis point. This is statistically significant. This is meaningful difference. This is a meaningful difference, right? On a monthly basis, then the monthly continuously compounded rate would be 1%. Because if it is 12%, periodic rate is simply divided by 12. And is monthly 12%, 1%. Try that, and then and if you and try this, if you do I have it? And the point is, you might, as I said before, dividing, I mean, think about it. Dividing, 12% by 12, getting 1%, and then if you compound it, you will get close to this. Not exactly, but close, right? Close to this. Roughly equivalent to approximately, right? I mean, this is something, we already know, I mean, Finance 100, material. The reason I brought it up was, this is supposed to be I mean, if you divide it by 12, then it's like a simple interest. Yeah, that's why, there's a difference between, APY and, APR. So then effective monthly rate would be, again, by doing this and subtract 1, then the effective monthly rate, the difference between effective monthly rate and continuously compounded rate is 0.0005, which is insignificant. It's very trivial. There is hardly any difference, right? Therefore, for shorter periods difference, right? It's even smaller still, like, weekly, daily, right? So when continuously compounded rates are normally distributed exactly, that means effective rate over periods up to a month is equal to continuously compounded rates. And this is the reason why we have to use the continuously compounded rate, because continuously compounded rate is normally distributed, right? It has normal distribution properties. Now, so a continuously compounded rate is the function of time. That means, in other words, continuous compounded, all the rates are basically a function of time. In other words, the longer the maturity, right? The longer the holding period, longer the maturity, the greater the discount rate. The longer the maturity, the greater the interest rate, right? So they are direct. Being function means it's a direct proportion. It's in direct proportion to time. And square root of the variance of the continuously compound rate, variance of the returns rates are also function of time. However, the standard deviation of the returns are not function of time, right? Why? Let's take a look at it. If annual compounded annual return, continuously compound return, and if the standard deviation of annual return is 0.2, and the variance of the annual return will be 0.04. It goes without saying, 0.2 times 0.2 squared, right? 0.2 times 0.2. And the quarterly variance would be 0.01. And then quarterly standard deviation will be 0.1. But what would be then monthly standard deviation? Comes to 5.77. Why? Well, try this. What would be the quarterly? I'll put, subscript there, quarter. No, maybe. This would be better. Continuously compounded rate, quarterly rate. We have that quarterly, so actually what I'm trying to say is monthly, right? What will be the first of all, then what will be the monthly return, variance of the monthly return? Oh, it's easy. It's going to be quarterly variance divided by 3. If you do that, um, what do you get? Of course, that will be 0.003 something, right? Because you're dividing. And then you take the square root of that. Take the square root of that. What's it gonna give you? If you take the square root of that, it's gonna give you 5.77%. Right? So what did you just do? You took the square root of the monthly variance. Right? So what is that telling you? Variance grows in direct proportion to time, which means it's the function of time, but the standard deviation grows in proportion to the square root of time. Therefore, of standard deviation of continuous compound return is a function of square root of time, and that is also obvious from this too. Square root of this is this. Square root of this is this, right? So that brings us to our, that brings us to that prepares us. That gave us the tool to verify whether our scenario analysis, the result of our scenario analysis, is normally distributed, follows normal distribution or not. Okay, that verification will be done in our next session. So I'll see you guys in the next video. Stop recording.